afternoon, everyone. Myself, V. Krishna, Veni, working as assistant professor in the Department of Physics from Marri Laxman Reddy Institute of Technology and Management. So, up to now, I have completed 4 modules. From the quantum mechanics and solids, quantum physics is over. The second chapter is solids. So, let us go for the chapter 2 in the quantum physics and solid, that is solids. So, here the solids are free electron theory. So, other name for the solids chapter is free electron theory. Suppose if you take any solid, that is metal, semiconductor, magnetic material, insulator, whatever be the material you can take in the form of a solid. So, this solid, it may be suppose a copper. Suppose if you take a copper, so it will allows the current pass through it. The material which allows the current pass through it, then that material is known as metal. Example for the metal is copper. So next one, if you take a glass, that is glass, we can see the image of the object. So that is optical properties. The metal which allows the current pass through it, that is the electrical properties. Next one, glass, we can see the image of the object, that is a reflection, refraction, that is optical properties. Suppose if you take a ferromagnetic material, that is copper, uh, the material is a ferromagnetic material. The material can be magnetized, that is by application of external magnetic field, that is a magnetical properties. So different property, that is thermal properties. Some of the material get heated very fast, some of the material is not get heated very fast. So that is thermal properties. So different properties like electrical, thermal, optical. So these are all properties can explain only one theory, that is known as free electron theory. So the free electron theory was developed in 3 stages, that is classical free electron theory, quantum free electron theory and zone theory. So the 3 stages of the theory is, one is classical, quantum free electron theory, zone theory. Suppose the 3 stages of the free electron theory was different scientists was developed these 3 theories. The first one is classical free electron theory. So classical free electron theory was proposed by Lorentz and Drude in the year 1900. According to this theory, metal contains, so this theory was explained only the properties of the metals but not semiconductor and insulator. So it explains only the properties of the metals, and in this the free electrons are responsible for the conduction and which obeys the laws of classical mechanics. So classical mechanics, based on the classical mechanics, the free electron theory was explained by Lorentz and Drude. In this, the free electrons obey the laws of the classical mechanics, that is Newtonian mechanics. This is entirely based on Newtonian mechanics. Next one is, next stage of development is quantum free electron theory. So in this quantum free electron theory was developed by the Sommerfeld in the year 1928 based on laws of the quantum mechanics. And next one, according to this theory, the electrons move with a constant potential. In this case, in classical free electron theory, it does not talk about any potential, but here it was taken the assumption that it move in a constant potential. So this is the second stage of free electron theory. The third stage of the free electron theory is zone theory. So the zone theory was first developed by Bloch, the scientist called Bloch, and later was extended by Crony and Penny. So Crony and Penny was later extended this zone theory by Crony and Penny. First initiation by only the Bloch in the year 1928. And next, the theory, other name for the zone theory is band theory of solids. So before this theory, we don't know how the bands are formed in a solids. So after invention of this theory only, we came to know what is a band structure, what is a bond structure, how the materials are classified based on the band theory, that is conductor, semiconductor and insulator. So after the development of the zone theory only, we can able to differentiate between the materials called conductor, semiconductor and insulator. So these three are the stages of the free electron theory. So these three stages was explain all the properties of the solid, like electrical properties, the current, resistivity, conductivity, optical properties, the reflection, refraction, diffraction, and next one is magnetical property, that is permeability, susceptibility values, how it will be for different materials of magnetic materials. And these are the properties was explained one theory, that is the free electron theory. This free electron theory is in developed was in three stages. One is classical free electron theory, quantum free electron theory, and zone theory. So classical free electron theory, Lagrange and Drude; quantum free electron theory by Sommerfeld; and zone theory was developed by the Bloch, and later it is extended by Crane and Penny. So next, first stage of the free electron theory, that is classical free electron theory. So in this we have the what are the assumptions taken by Lagrange and Drude, what are the success and what are the failures. So now we will see. So the free electron theory for only the metals. So which was based on the laws of the classical mechanics. Suppose if you take a metal, suppose metal is in the example for the metal is copper. Suppose if you take a copper, the copper metal is composed of copper atoms. Each and every atom its a outermost electron, that is valence electron. So these valence electron is not only belongs to a single nucleus but also belongs to all the nucleus existing in the metal. Suppose if you take a copper, so this is a copper metal, and in this we have the lattice ions, that is nucleus. So the copper metal is composed of copper ions. So each and every atom there is its outermost electron. So each and every nucleus have its outermost electron. These electrons are revolve around the nucleus throughout the material. So these electrons are obeys the laws of the classical mechanics based on the MB statistics. MB means Maxwell and Boltzmann distribution. Means one level n number of particles can exist. So here in a single level, not only two, any number of, that is infinite number of particles can exist in a single level, that is MB statistics. And here the atom, the electrons are free to move throughout the volume of the metal, and which is like a molecules of a perfect gas in a container. So these electrons are formed like a molecules of a gas in a container, and this collection of valence electron from all the atom in a given metal forms a electron gas. These electrons are free to move throughout the metal, and here the collision between positive nucleus, the collision between positive nucleus and negative electron, the collision between positive nucleus and negative electron is elastic in nature. So what is elastic means there is no loss of energy. So here there is no loss of energy between colliding the positive nucleus and the negative electron, and these electrons are move in a random direction. So the resultant current is zero. So without, by application of external electric field to the metal, then what will happen, these electrons are move in a direction opposite to the direction of the electric field. So these are all assumptions of the classical free electron theory. So first assumption is electron revolve around the nucleus and metal is composed of such nucleus, and these electrons are formed like a perfect gas in a container, that is electron gas, and these electrons are moved throughout the volume of the metal. And next here the collision between the positive nucleus and negative electrons are elastic in nature, that is no loss of energy, and it obeys the classical kinetic theory of the gas. The electrons in a metal obeys the laws of classical kinetic theory of gases, and also it having the velocity of the metal, the electron velocity in a metal obey the classical Maxwell Boltzmann distribution of velocity, that is MB statistics. N number of particles can exist in a single level. Next, the free electrons move in a completely uniform potential field due to the fixed ions. So here this uniform potential provided by the fixed ions in the crystal. If you take any crystal, the positive ions are fixed in the metal. This will provide a uniform potential due to ions fixed in a lattice. And here the electron, each and every atom has its own electron, valence electron. These valence electrons are moved randomly without electric field. By application of electric field, these electrons move opposite to the direction of the external electric field. So these are the assumptions taken by the Lagrange and Drude, that is known as classical free electron theory. So now what are the success behind the classical free electron theory? The first success is it verifies the Ohm's law. So Ohm's law, it verifies the Ohm's law. Next one is Wiedemann-Franz law. So Ohm's law is what? V is equal to IR. If you take any metallic wire, if you apply a potential to the metallic wire, then what will happen? The current is passed through the material. That current is directly proportional to voltage. So that is V directly proportional to I. V directly proportional to I means V equal to I into R, where R is the resistance and I is the current and V is the potential applied to the material. So it V is equal to IR formula, that is the Ohm's law, which was verified by using the classical electron theory. Next one, Wiedemann-Franz law. Wiedemann-Franz law explains the thermal conductivity. It will give the relation between thermal conductivity and also electrical conductivity. It relates the thermal as well as electrical conductivity. The Wiedemann-Franz law explains the relation between thermal conductivity and electrical conductivity. So thermal conductivity means the capacity to heat the material is known as thermal conductivity. Electrical conductivity, the capacity to pass the current through the material is known as electrical conductivity. Between these two, there is a relation. That relation was explained by using the success of classical free electron, that is Wiedemann-Franz law. Next one is electrical conductivity and also thermal conductivity. These both the properties was explained by using the classical free electron. That is the success of the classical free electron theory. And not only thermal and electrical but also optical properties of the metal. So these are all success of the classical free electron theory, that is thermal, electrical, optical properties, and the relation between thermal and electrical conductivity, that is Wiedemann-Franz law, and also it verifies the Ohm's law. So these are all success of the classical free electron theory. Now what are the drawbacks and what are the failures of the classical free electron theory? The first failure of the classical free electron theory means it does not explain the photoelectric effect, Compton effect, black body radiation. So does not explain these three effects by using the classical free electron. That is a failure of the classical free electron theory. Next, second failure is does not give any correct value of the specific heat of the metals. So the specific heat of the metal is value is 4.5 into Ru, where Ru is the universal gas constant. So this value is by experimentally it is equal to 3 by 2 Ru, but actual value is 4.5 Ru. So next, but actual here it is 0.01 Ru. So there are three discrepancies are there. So three values are differ. So that's why it does not explain any correct value of the specific heat of the metal. Next, third failure is electrical conductivity of semiconductor as well as insulator. Means it explain only the metallic properties but not semiconductor and insulator. Next one is the K by sigma T, where K is what? Thermal conductivity. Sigma is electrical conductivity. K is known as thermal conductivity and sigma is electrical conductivity. K by sigma T, that is K by sigma T is constant, which is known as Wiedemann-Franz law. This Wiedemann-Franz law does not explain the value of the thermal and electrical conductivity at constant at low temperature. The Wiedemann-Franz law fails at low temperature. And next, fifth failure is the ferromagnetic material having some susceptibility. The susceptibility also could not have any value by using this theory. Could not explain the ferromagnetic theory, as well as susceptibility of the paramagnetic is greater than the experimental value. Actually, paramagnetic material having the susceptibility which is greater than the experimental value. This is also a discrepancy between the actual as well as experimental value. So these are all assumptions that is made by the Lagrange and Drude. And next one is we have the advantages or success, and next one is failures or drawbacks. So next development of the free electron theory, second stage of development of the free electron theory is quantum free electron theory. The quantum free electron theory was proposed by Sommerfeld in the year 1928 based on the laws of quantum mechanics, and also it obeys the laws of the Fermi-Dirac statistics. So whereas previously it is a Maxwell-Boltzmann, but here it is a Fermi-Dirac statistics. Fermi-Dirac statistics says that only two electrons are exist in a particular level, that is Fermi-Dirac statistics. But MB is n number of particles can exist in a single level is known as MB statistics. FD is only two electrons can exist in a single level, that is FD statistics. So previously it is MB, but here it is FD. So that is the difference between made by the Sommerfeld between classical and quantum free electron theory. So this is what introduction to quantum free electron theory. Now what is the assumptions made by the quantum free electron theory? So here the valency, suppose here also same the metal, here also the second stage of the free electron theory also was explained only the metallic properties, metal and its properties, but not semiconductor and insulators. He classical free electron theory, quantum free electron, they both are explained the only the properties of the metals but not semiconductor and insulator. So now again if you are taking the metal, any metal, that is copper, ferrous, iron, whatever be the metal you can take, that metal is consisting of valence electron in a atom. Each and every metal, suppose again I am taking, suppose sodium is a metal. Sodium is composed of sodium ions or sodium lattices. So these sodium lattices having the valence electron. Suppose sodium is our electronic configuration is 1s2, 2s2, 2p6, 3s1. So these are all fulfilled with the orbitals, and here it is a incomplete orbital, that is one electron only occupied in a single level, that is next one more electron has to occupy if you want to get the stability. That will be act like a free electron in its outermost. These free electrons are moving inside the metal, throughout the metal. It is not escaping from the surface of the metal. So that is the metal surface is act like a boundaries. That is boundaries is known as high potential. It is act like a high potential. So hence electrons are trapped inside the potential, means this metal is act like a potential well. The distribution of electron in various allowed energy level occur Pauli's exclusion principle. So here it was made by the assumption FD statistics, also Pauli's exclusion principle. So what is Pauli's exclusion principle? No two electrons cannot have same quantum number. So orbital quantum number, azimuthal quantum number, spin quantum number, magnetic quantum number. So different quantum numbers are there. So that quantum numbers are differ for single electron. No two electron. One electron have 4 quantum numbers. Again one more electron if you take, that is also having, that will be quantum numbers are differ. Means no two electrons does not exhibit same quantum numbers. That is the Pauli's exclusion principle. So here based on FD as well as Pauli's exclusion principle. This will follow the electrons will follow the FD statistics as well as Pauli's exclusion principle. So next one, the attraction between positive nucleus, negative electron is negligible. We can neglect the attraction between positive nucleus and negative electron. But also positive repulsion between positive nucleus, negative electron, the repulsion between same charges, that is positive negative. The attraction between positive nucleus, negative electrons is ignored, means negligible. That is assumption, third assumption. The fourth assumption is the distribution of energy among the free electron is according to Fermi-Dirac statistic. That is only two electrons can exist in a single level. That is Fermi-Dirac statistic. In quantum free electron theory, the energy of the electron is quantized. The quantized means what? That is the energy having only discrete energy. The energy is quantized means it is having only discrete energy, not continuous value. It is a discrete value. And next one is the possible energies of the electron from the Schrodinger time independent wave equation. The particle in a potential box, what is the expression we will get from the quantum physics, that is E equal to n square h square by 8 ml square, when n is the quantum number, h is a Planck's constant, m is the mass of the electron, and L is the width of the box or width of the potential well. So these are all assumptions made by the quantum free electron theory. Next one again we'll move to the success. What are the success of the quantum free electron theory? It also same explains the thermal and electrical conductivity for only metals but not semiconductor and insulator. And next one is thermoionic emission. The thermoionic emission means if you take any filament that will be get heated, then what will happen? The ions will be emitted from the filament, that is thermo, but is using the thermal energy, the ions are emitted, that is thermoionic emission. To explain the thermoionic emission, that is phenomenon was explained by quantum free electron theory. And next one, temperature dependence of conductivity of metal. So the metal temperature conductivity, how the depends of the temperature, conductivity of the metals based on the depends on the temperature, how it will be also explained by the quantum free electron theory. And correct value of specific, there it is a discrepancies between the actual value, experimental value, theoretical value, but here exact value of specific heat of the metals. So what is specific heat? If you want to heat the 1 gram of material, 1 gram of material to 1 degree centigrade temperature, then the required temperature is known as specific heat. So 1 gram material get heated for 1 degree centigrade, the heat required is known as specific heat. That also explains the quantum free electron theory. Susceptibility value. Susceptibility was there, it is a discrepancy that is greater than actual value. But here there is a correct value of susceptibility of the metals. There it is not explained the photoelectric effect, but here it is was explained correctly, black body radiation, photoelectric effect and Compton effect. So next, according to this theory, only two electrons are responsible for conduction. That is not true. That is a drawback, come under in the drawback. So next one, drawbacks of the quantum free electron theory. So why it is explained the some, why it is not unable to explain metallic properties exhibited by only certain material. Why wood does not conduct the electricity? Semiconductor it conduct the electricity partially. Why it is conduct the conductivity by metals only? Why? What is the reason behind it? That was not explained by the quantum free electron theory. Next, it is unable to explain atomic arrays in a metallic crystal should prefer certain structures only. Some of the materials exhibit the simple cubic. Some of the materials exhibit the FCC, that is face centered cubic. Some of the materials exhibit the BCC, that is body centered cubic. So why it is? Why? What is the reason? Why it is choosing only BFCC? Why it is choosing only BCC? Why? What is the reason? That also does not explain the quantum free electron theory. And third disadvantage or failure is we cannot distinguish between metals and non-metals. Metals, non-metals means semiconductor and insulator. Metal means conductor and non-conductor, that is non-metals. So the distinguish what is the differences, that also does not explain by using the quantum free electron theory. Next, it is fails to explain the positive value of Hall coefficient. So positive Hall coefficient is p-type semiconductor, negative Hall coefficient is n-type semiconductor. So it does not explain the positive value of the Hall coefficient. Next, according to this theory, only two electrons are responsible present in the single level. Why it is? And for these, that electrons only responsible for conduction. Why? What is the reason? Why only two electrons are responsible? That also could not explain by using the quantum free electron theory. So these are all two stages of the free electron theory. First theory is classical free electron theory. Second theory is quantum free electron theory. Third theory is zone theory. So each and every theory has its own assumptions, advantages, disadvantages. Similarly for quantum free electron theory also there is a advantages, disadvantages and failures. So each and every theory we need to write. So assumptions, advantages, disadvantages. So similarly quantum free electron theory also there is a assumptions, advantages and disadvantages. So next class we will discuss about the zone theory, that is third stage of free electron theory, that was proposed by the scientist called Bloch in the year 1928. That is also based on the quantum mechanics, based on the laws of the quantum mechanics. So next class we will see the third stage of theory. Thank you. So I have referred this topic from these books. Thank you.